All right, so your assignment number 1 has been released. I believe it's due next week, which will be the reading week. Try to get it done as soon as you can. Your programming test 1 is going to be primarily based on that. I'll give you guys some guide, maybe at least 1 week before the test, so you will know what to expect. And tutorial number 5 has been, material has been released. I just didn't announce it. So you can look for mathematical induction, the trinomial restructuring after deletion. That could be very useful for you to get some more inspiration about how to implement the rotation for assignment 1. And also we talk about the one-line construction of the binary tree. It's actually a very important line to really understand. So in your programming test 1 as well, you will be given expectation about what each method should really do. And the very typical way is to give you a tree before and after the operation, right? So that's something you definitely want to make sure you're comfortable with reading it and also writing it, both of them. Okay, and this week's, we got one more tutorial before the reading week. I haven't decided yet exactly what we're going to do, but I think most likely, since I'm going to introduce to you about depth-first search, which is very interesting stuff to really have, and we got lots of things to explore about depth-first search. And I think a tutorial this week, we can do some extra exercise, maybe some complicated one, which we may not have the time to do in full scale in the class. Okay, I'll keep you posted. Okay, any questions about the course? Right, just remember for this course, we don't have any assessment until after the reading week. But after the reading week, we do have 3 tests coming. Do check your calendar, okay? So they're coming. All right, a very quick recap, and then we'll get started, okay? All right, so last time we basically just went on to talk about more terms, definitions for graph. Right, so I think one of your fellow students asked about one-node graph, very special, so you just want to keep pay attention to it. And also, whenever you're given some properties of the subgraph, so these are the 4 aspects we have talked about so far. So we're going to do a summary table in a moment. Okay, we'll do that. Okay, that's something hopefully maybe you did a little bit, maybe over the weekend. If no, that's okay. Let's go over the answer. And we talk about spanning subgraph. What does it really mean for subgraph to be spinning? Just cover all the vertices. And we talk about just spanning subgraph versus subgraph, right? We spoke about it, and make sure you will be able to distinguish which one is much more specialized than the other, and how can you find a witness to really disprove the other one, right? That's something we also spoke about last time. And we talk about connection. What does it really mean for a graph to be connected? Basically, for every pair of 2 vertices, you're able to find at least one path in between them. So that will be connected. Otherwise, you will not be connected. If you can find at least one pair of 2 vertices such that there's no path between them, the graph is not connected, right? Simple definitions, but you're going to make sure you know clearly which one is which. And connected components. That's also something we spent quite a bit of time on last time. So the maximum here is very important. That means the connected component is such that you cannot expand any further by taking another edge to reach out to one more vertex, just maximum. And the best way to see that is visualize it, right? You can see in this example here, this one here, CC1, you just cannot expand this connected component by including one more vertex because there's no such edge, right? When we first presented that, right? So that's really the maximal part. And we spoke about what will be the minimum number of extensions for you to actually connect the connected components so that the whole graph becomes connected, right? So it depends on how many connected components you have, just -1. That'll be the number of extensions you need. Try to generalize as well. Sometimes I may not generalize it based on the example. That's something you should also do when you try to look at the study materials. All right, and then we'll talk about forest versus trees. Forest will be anything that's acyclic, basically, any subgraph. Very simple definition. And for trees, we're adding one more criterion, which is the forest must be connected at the same time. In that case, you can call the forest a tree as well. That's why you can see trees is much more specialized than forest. And this is basically, okay, this is basically what we were at. There was one announcement I made last night, just about this page specifically. When we talk about a choose operator over here, 56, so that one there is not exactly about the number of spanning trees. So please do read through the announcement I made last night. I did make some clarification. And if you really want to formulate about how many spanning trees are possible, in that way they will require something that's much more complicated, which we don't have to worry for this course. But do read my announcement. I think there will be some important points you want to pay attention to from there. All right? And spanning tree. And just remember, if you do have a spanning tree, that means the number of edges will be the number of vertices minus 1. Okay? It's a very important property you will see all the time. We'll see that again, just to see more examples. Any questions about spanning trees? All good? All right. Let's now move on to this table here, right? So we can summarize about what we have talked about so far. Okay. Let's talk about this one here. Right here. Okay. So we got 4 turns so far. We got subgraph, spanning subgraph, forest, and also tree and the spanning tree. Okay, actually somehow I missed one separator here. Okay, beg your pardon. Forest, tree, and spanning tree, right? So these are the stuff. And then for each one of them, we're just going to evaluate it against undirected or not, acyclic or not, connected or not, or spanning or not. Right? These are the criteria we're going to look at. Okay? Let's just start with. All of them we assume to be undirected, beg your pardon. So they're all undirected. So check means they should be satisfied. All right? That's good. And let's now talk about how about we can go, I would say when you study for this, maybe you can create an empty table. You can either go for row by row or column by column, right? They can show you different aspects. Let's go column by column. Okay, so we can just make each concept self-contained. Now for subgraph, right here. The question is, does it need to be acyclic? Not really, right? Think about what's really the definition for subgraph. So if you recall that, subgraph, we are only requiring that the V prime is a subset of V, and also E prime is a subset of E. That's all we care. Whether or not it's going to create a cycle, we don't care. And also whether it's going to create a connection, we also don't care. Whether or not it's going to span through all the vertices, we also don't care. So subgraph is really very weak notation about what a graph can be. Okay, so in that case, not necessarily. So I'll say question mark, question mark, question mark. So maybe, maybe not. The only thing we require will be undirected. Okay. How about spanning subgraph over here? Well, apparently it has to be spanning, right? Otherwise, it wouldn't have the name. So it's going to be spanning. Does a spanning subgraph need to contain no cycle? Not really, right? It's orthogonal, it's independent criteria, okay? Not really. Also, a spanning subgraph also doesn't need to have any connection. Again, you want to go back to the very definition. Whenever you are given something that's beyond definition, you want to start with definition first to see what the definition say. And for spanning subgraph, all we care is the vertices, V prime, will be exactly equal to V. That's all we care. Whether you have cycle or not, whether it's connected or not, we don't care. Right? But it got to be spanning. All right, let's count for forest and tree. How about forest over here? What's the definition of a forest? Yeah, go ahead. Has no cycle, should be acyclic for sure, right? So that means at least we should check this acyclic. And we know that a tree is also a forest. So a tree also should be acyclic, right? This time we can do 2 columns at a time. All right, good. Now, for forest, does it need to be connected? Not really, right? Yeah, I think we have seen some example. In order to be a forest, there might be some vertices isolated from the rest of the world, from the rest of the forest, okay? However, this is something important here. So forest does not need to be connected. However, a tree must be connected. That's really the characteristic difference between the two. All right, good, okay. It's also good to actually do such comparison. Okay, notice about this particular intersection here. What about spanning? Does a forest need to be spanning? It's not part of the definition, right? We just simply say a forest is just a cyclic subgraph. So whether or not it's spanning, we don't care. And we also don't care about the tree either, okay, being spanning. All right. So for these two, also we don't care. Either way is okay. We're going to see more examples today about different possibilities. We'll see, okay? Just more examples. All right, the last column, which is the most demanding notion about a graph, which is a spanning tree, right? A spanning tree obviously is a tree for sure. So in that way, it definitely cannot be cyclic. Well, got to be acyclic for sure. And also, a tree also is connected by definition, so these two must be the case. So now, should a spanning tree be spanning? Well, it sounds like a no-brainer, right? Of course, because its name tells you it got to be spanning. There we go. Should you memorize the table? I would suggest not, because the way I'm going to ask the question in the test or the exam may not be just ask you about some very simple definition. I might, but I'm just saying there might be some other question you have to think through about what's going on here. So try to really synthesize all the definitions there, become more natural to you. That would be my suggestion. Any questions about all the terms? All good? Okay. Let's now put this aside, and then let's do some very quick exercise. Okay. So let's now, okay, these are on the slides, but I'll just put it here. Let's say we're given this graph. Not exactly complete, if you know what I mean. When you review the notion, we also got a notion about the graph being complete. But this graph here is not exactly complete. Think about why. Okay? So now we've got multiple choice, A, B, and C. Could be a single correct option, could be multiple correct options. So now which one or which ones is or are spanning trees? All right? And we can make it even more, a little bit more demanding from you. In addition to just choosing which one or which ones are spanning trees, the other ones you should explain why it's not spanning tree. Right? Diego, go ahead.
C would be a spanning tree.
Okay, first of all, let's verify that. I agree. So C is a spanning tree. Okay, so that one is the correct answer. I agree. Okay, first of all, you can see it is spanning with respect to the original graph. So you can see we can see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Apparently, it is spanning. Does it contain any cycle? No. Is it connected? Yes, because if you choose any two vertices, they're always connected to each other. That's great. Okay. Awesome. So let's just put some justification, right? I think that will help you when you do the study. So it is spanning, cyclic, and also connected. Another option that will be a spanning tree? No. Okay, good. So let's now justify why A is not a spanning tree, also why B is not a spanning tree. Diego, why don't we start with you first, and now I will call you. Yeah. How about from A?
A has a cycle.
Obviously, right? Awesome. Okay. First of all, this one here is also spanning. All the vertices are covered. Also, it's connected. Connected all the between every two pair of vertices, but it's a cycle. 1, 2, 3, 4, 5, right? It's a cycle. All right. So that one there, spanning, connected, but cyclic. Would you like to give it a try for option B? Why is it not a spanning tree? Because it's not spanning. Awesome. All right. Because you can see only cover 4 vertices, but in the source graph we got 5. All right. Awesome. Okay. So for this one here, it is connected. As far as all the vertices in this subgraph is concerned, it's connected. And then no cycle. And also, but it's not spanning. Okay, you can see this one's missing somehow, right? Right, more like a visual example, right? All right, any questions? Okay, all right, let's now move on. Let's now talk about some more properties for the graph, and then we'll move on to graph traversal. Okay, let's do one more set of example, right? Just enough, right? So last Thursday, we spoke about this particular property over here. And if you guys remember, right, it's very important. When I say something if something, I'm really saying this property here implies this property here. All right, let me write it down again. Okay, this one is really saying G is a spanning tree implies n equals n minus 1. The other way, we don't really care for this property here. May not be right, may be right, but it's not a focus. Okay. We already proved by mathematical induction last Thursday in the tutorial. Make sure to review it. You can try others as well. Okay. This one here, I can tell you, it's actually not a property. Turns out, okay, and then we'll talk about it. Okay. So this is why whenever I give you a property like a candidate property, I may just want you to prove and disprove it. Right? We'll get to the disproving the last property in one moment. I'll give you some hints. I'll give you some example as well. Okay. So this is not true in general. Okay, we'll get there. And let's now look at spanning tree, forest, and connected. Just give you more example, right? You guys can maybe study a bit more carefully later, but let's just see more. Okay, and then I'll try to draw more connection from the example itself to the relations that we are putting over here, right? You can see, for example, here, this is very strict, just about exactly equal to, if the graph happened to be a spanning tree. However, this one here is saying either less than or equal to. So I'm going to give you both cases as example. We can see some property, sub-property from there. And also similarly, for this one here, it can be either greater than or equal to. I'm also going to give you some examples as well, right? Just to see what if you go for one, like for equal sign, but or if you versus if you go for the larger than sign to see how they are supposed to be different. Okay, let's start with something we're quite familiar. Just one more. Okay. So let's start with this one here. So I want a spanning tree. So the one I have on my notes goes like this. So let's say I got AC here, CD here. So far, 3 vertices are connected. In order to create a spanning tree, I want to make sure I connect the other vertices too, right? Oh, actually, let me connect these first, right? Okay, let's say these 3 are connected already. I want to connect to 2 more. But I can get different choices over here. For example, I can now connect to B this way, but maybe I can connect to B this way. And I can connect to E this way here. And I can connect to E this way here. So both cases, I got spanning tree. Okay, so now in this case, you can see n equals n minus 1. Okay, n will be the source, the number of edges in the spanning tree. Implicitly, of course, as I said last time, when you create a subgraph, it would be as if these edges from the source graph was not chosen. So they should not be there, right? Just make it more explicit. Right, just take one to check the property. So m here will be 1, 2, 3, 4, 5. n minus 1, 1, 2, 3, 4, 5, 6. 6 vertices minus 1 will be 5, right? Works. Spanning tree. But that's something we already proved last Thursday. Just use one more example to verify. Okay, let's now take a look at the next one. Let's say we want to create a forest. And a forest, by definition, simply say there should be no cycle. However, it doesn't really say if that should be connected or not. So I'm going to give you 2 possible forests. One will be connected. The other one will be not connected. All right, let's see. So let's see the one that will be connected. So let's say this one here. This one here. Let's say this one here. Okay, it's connected. So that means these edges were not chosen. So this, you can think about this forest over here has only one single connected component that's acyclic. Okay, I'll write it down. So this is one single acyclic connected components. Given that it's connected, it's also spanning at the same time. Connected, also it's spanning. Right? You can see covers because all the vertices are connected. Of course, you got to cover all the vertices, right? So this direction is going to work. But let's see another possible forest, which you might see more often. Okay. Let's see the other one. Okay. And then I will draw some relation to the numbers just in one moment. Let's see the visual example first. Another forest would be we got more than one acyclic connected components, more than one. Okay, maybe two, let's say. So what we have is, so let's say this one here, this one here, this one here. This is one connected component. This is another one, meaning that I'm not choosing all the rest of the edges. They are crossed out. So you can think about, we now have two acyclic connected components. One is over here. Another one is right here. So we have two acyclic connected components. And this is a very nice counterexample to show that when you actually got spanning, it may not be connected. Spanning implies connected is not in general true. And you can think about this is one witness for that. Right? You can see spanning, it covers 1, 2, 3, 4, 5, 6 vertices. But at the same time, it's not connected. All right? Notice about these two implications. All right? Okay. So that one's good. All right, let's see the numbers. Okay. For forest to be exactly connected, so here you can see 1, 2, 3, 4, 5, exactly n minus 1 edges, exactly. Okay, so that's something I'll write down here. So the number of edges in the forest will be exactly equal to the number of vertices minus 1. If the forest also happen to be spanning, in that case, it's just a spanning tree. But not necessarily every forest is spanning tree, not necessarily. Some cases, yes. All right, just be careful. Right? Another one would be if we got exactly n strictly less than n minus 1, because you can see 1, 2, 3, 4. 4 is strictly less than 1, 2, 3, 4, 5, 6 minus 1. Right? So you can think about here for the forest, we'll talk about if the equal sign here is true, that means it's connected. But if the less than is true, it's not connected. That's what we're saying. Okay. It could be a little bit confusing when you see so many things, right? That's why you really gotta sit down, okay, isolate it, and study, okay, and get yourself convinced. Okay, one more. Let's get on to, let's say, when the graph is connected. When it is connected, it could be cycle-free, or it may contain a cycle. So these are the two things we're gonna explore. All right. So let's say given that it's connected, one example would be, let's say AB, this one here, just the same, it's okay, just connected. So this is a connected graph without a cycle. Where n is equal to n minus 1, right? You can see it's connected, but it's acyclic. Oh, sorry, let me swap the order, I beg your pardon. Somehow it's a little bit different from my notes. I really meant to say acyclic. Okay, this one acyclic. Doesn't really matter, but if you know. Okay, let's do that. Okay. And then you can see that when it's connected, the lower bound is when n is exactly equal to n minus 1. What if it's larger than? That means we're adding more edges to the graph. Right? So let's say we already got this one here. That one is connected without any cycle. But we want to add one more. If I want to add one more, I don't have many choices. I can either add this one here, I can add this one here, or I can add this one here. Doesn't matter. You're going to create a cycle. Okay? Let's say I add this one here. Okay? So this one here creates a cycle. So this will be the case where n is larger than n minus 1. 1, 2, 3, 4, 5, 6. 6 over here, larger than 6 minus 1. We got 6 vertices, right? Right, I think there's something you really want to do is, follow this kind of idea here and make your own example for the different terms, right? Final one. Right here. All right, given that a graph has a cycle. However, it does not necessarily imply the number of edges is always larger than or equal to n. We're missing one condition here. I'm just going directly to the property here, right? So here, we are saying this. Cyclic implies n larger than or equal to n. This is not true in general. Turns out we are missing one antecedent, like assumption about the graph. Well, actually, the assumption is one of the properties that we spoke about on the directed graph, actually. Okay, turns out, okay, missing antecedents. Missing antecedents or assumption. Connected as well. You can only say that if the graph is cyclic, also is connected, then this one is true. That will be right. You can also prove it using mathematical induction. Okay? I'm just saving some time to tell you the answer already, but you can forget about what I just said. You try to look at the property again, try to convince yourself to see if you can come up with any counterexample. Okay. Right. I'll help you a little bit about come up with some witness. Okay? So we're saying that the original one here is not a property. So what we'll do is, how do we give a witness? Back to your math review lecture. If I have an implication, how can I show that the implication is false? If I say P implies Q, to disprove it. What should I do? True implies false. I agree. That's the only way to actually make the implication false. Exactly. So we got to take that assumption about the graph being cyclic, and then we show that it's possible for a cyclic graph to not satisfy Q, which is being n larger than or equal to n. Exactly. Thank you. Good. Right. You can see many things kind of put together. Right. That's why the math review lecture is so important. All right. All right. So here, to disprove it, assume P. And then you want to show that Q is not the case. Okay. So for this one here, I'm going to give you a little bit hints. Actually, one example as well. So this one here, witness of violation. If you can give me a graph that's cyclic, at the same time, the graph happened to be not connected. Connected or not, it's not part of the property, so I can just arbitrarily choose one, right, for the witness. Not connected. And then I can also show that it is not the case that n is larger than or equal to n. So what I'm doing here is, I'm trying to say, I get something that's cyclic. However, I can end up showing to you that this is not the case. Of course, there's some intermediate condition that the property doesn't care. I just fix it for the witness. All right? Okay, I'll just give you one example here. So this will be one counterexample. Let's say I got a graph that looks like this. Let's say it's more like a triangular shape graph. And then I have another isolated node right here. First of all, you can see there is a cycle, for sure. Cycle right here. Not connected because this node here is isolated. However, if you double check n larger than or equal to n, it's false. Double check. I'll leave that to you. All right. So this will be, I kind of gave you the witness already, but you may want to decide some witness may not be appropriate, some witness may be appropriate, right? Things like that. You want to just get yourself used to coming up with things like this. This will be the last set of example I would like to talk about for all the turns so far. Any questions? Okay, ready for depth first search? Okay, there's something I want to, since I got a diagram already, there's something I want to talk about very quickly. The depth first search we're going to talk about is going to be applied to any arbitrary graph. So the graph itself may or may not be connected. So this will simply mean you may need to take more than one passes to really do the depth first search. Each depth first search, I will mention a term either today or on Thursday. It's called the depth first search forest. Okay, so let me just use this one here. You can feel free to take a notes, and that might be a little bit, that could be useful. Not useful for now, but maybe after 1 or 2 lectures. Let's say I got this graph here. It's a forest that's not connected. Somehow I want to visit all the vertices and edges, somehow. When I start with here, I will be able to depth first search to all the vertices in this particular connected components. That's one. However, as soon as I'm done with the current depth first search, I still got more vertices to be visited. So that would mean I need more than one depth first search applications. So as you will see, maybe in assignment number 2 or 3, you will have to implement this kind of mechanism to see when you should really do more depth first search, as many as needed until you cover all the vertices. Okay? So there's something you will see later called depth first search forest, which means each time you're going to cover one tree at a time in a graph as you try to traverse the graph. That's something I will mention as well. But since I got a graph here, let's not waste it. Okay. Okay. We got about 7 minutes. I think we can talk some very quick idea, and then we can do some little example. And we can do the actual slightly more complicated one after the break. Okay. So let's get some principle understood. So on the slides, we are now done with 22 over here, okay? And basic properties, that's something we also explore. Okay, we're gonna start with slide number 24, okay? Graph traversal. So there will be 2. Let me write it down here. How about this? Just give you a little bit of roadmap. So graph traversal. We're going to learn about two kinds of traversal, however, but let me just say that, right? When we talk about graph traversal, so one will be depth first search, the other one will be breadth first search. And let me call it basic. And for the breadth first search, we're going to just talk about undirected graph. The basic depth first search is going to be about also undirected graph, which we'll cover today and also on Thursday. The more advanced, which I definitely want to cover as well. I didn't do it last semester, but I think you guys are lucky. I can give you more this semester. It's definitely worth knowing about the more advanced. Directed graph. And it is advanced in the sense that once you have done the traversal, we're going to do certain things called markings. You're going to mark each vertex by some color. You're going to mark each edge as certain edge, right? So give you a look ahead, right? So in the case of the advanced one, the vertices is going to have 3 different colors in transition. Just standard. I didn't make up the color. White, gray, and also black. Also, for edges over here, there are 4 kinds of edges we have to categorize. Okay? We got something called tree or discovery edge. And also back edge, forward edge, and also cross edge. All right, just a look ahead. I'm hoping that at least I can touch upon that. If not if not Wednesday for sure, when we come back from the reading week. So I will definitely make some questions for you to practice in the assignments. Okay, about the depth first search, the advanced case. We can maybe cover the basic case, possibly in the tutorial this Thursday. Okay. Right, this is something to look forward to. Right, we're definitely going to do enough coverage on this. Okay. Okay, what's really graph traversal? Very similar purpose for tree traversal. You just want to visit every node and every vertex and every edge. That's what you want to do. You want to do it systematically. So there are only 2 ways in principle, either depth first search or breadth first search. But in tree, we got pre-order, in-order, post-order, right? And typically, the running time, I can maybe talk about it once we get to some code later. But I can think about we're going to do it so systematic so that every vertex and every edge are just going to be touched upon only once. So overall, the running time would just be the number of vertices plus the number of edges. That'll be about the time complexity. So that'll be something we can assume. Okay. Okay, and applications. Okay, so this one here, I will delay a little bit because for now, we should really learn about how to do depth first search first before we get to anything that's more application oriented. So this will be just some example about, let's say if we got one graph right here, okay? And the graph has connected components number 1, connected components number 2. So that means we will need 2 applications of the depth first search. That's something I'll show you exactly, okay? But so these are all the standard questions you can answer after you have done enough number of depth first search, right? Something to do with reachability and also path, also minimum path, and also whether the graph is connected, spanning tree, connected components, also cycle. So these are all the standard questions you can just answer after you have done the depth first search properly. And similarly for the breadth first search as well. Okay? I'll delay this one a little bit later because application means given that the depth first search has already returned, how can you make use of it to really answer these questions? Let's now learn about how to do the depth first search itself, and then we'll come back to here. Okay? So I'll leave this one clean, so we'll get back there later. Okay, depth first search. Let's do a little bit of introduction, and then we'll take a short break, and then we'll do some tracing. Okay, I'm now going over some quick bullet point in slide number 26, very quick. Okay, just get some general idea. All right, so let's start with the name. It's called depth first search. And here we talk about undirected graph for now. Okay, undirected. Okay. And always, you should really specify about where would be the starting point of the depth first search. So, for example, in this graph here, and you can notice that this graph happened to be a tree. That's deliberate. I want our very first depth first search example to be so simple. We're only going to show you how you can keep discovering new vertices. Okay? So let's say the starting vertex would be A. So that means I might just notationally put A to be the starting point for the depth first search. So whenever you're asked to do some depth first search, very likely you will be given some starting point for the depth first search. If you were not given, you can start with any arbitrary vertices. Okay. Okay. So the idea would be we basically want to build a path from this starting vertex A, and then the way we're going to construct the path is by following incident edge. For example, you can see here, A here, there are three possible ways I can extend the path. I can either extend by taking this incident edge, or I can extend by taking this one here, or I can extend by taking this one here. Either one should be okay. However, usually in the test or exam, to just make it more like a stricter, for you to do the traversal, usually we'll say, what order should you follow when you actually do the incident edges coverage? I'll show you that once we get to the example, okay? But just so important for you to know that it's going to be following some incident edge. And the idea will be you want to go as far as possible. So what do we really mean by that, as far as possible, right? So there's some concept over here called backtrack. Okay? I'll try to do a little bit more like a hand waving, a little bit abstract, and then we'll try to get to the tracing. I'll re-emphasize again. Okay? So backtrack really says the following. And somehow you want to find the latest vertex that goes before that, right? So this one here, I don't need to ask you. So the standard way of implementing a depth first search, either you can do it recursively, or you can do it iteratively. But if you do it iteratively, you have to maintain some explicit stack to really help you keep track. So in the lecture, and also in the assignment, we're going to do the iterative version. But if you really want to try the recursive version, you can also try that. It's also very standard. But the thing is, if you do recursive version for the depth first search, there will still be a call stack behind the scene anyway. So stack is still there, right? So just be aware. So the data structure we're going to use is going to be a stack, which will be last in, first out. Right? That's what you learned from 2101. We're going to use it. Okay? And then let me just say one more thing about backtrack. Okay? It goes like this conceptually. I'll put it here. Let's say currently I am handling this particular vertex. Let's say I'm here. And then let's say there are three incident edges from V. Let's say we got X, we got Y, and then we got Z. We got three. X, Y, and Z. Okay? X, and then we got Y, and then we got Z. Let's say we're going to follow the incident edges in alphabetic order. So we're going to handle X, some subgraph over here, and also handle Y, some subgraph from there, and then handle Z, some subgraph from there. Okay? You can think about this on cloud right here. So from X, there could be some cloud. From Y, there could be another cloud. From Z, there's just going to be another cloud, okay, in general. So let's try to make it a little bit abstract over here to imagine, but you will see that exactly how it's going to happen when we do the tracing. So there will be a stack at a runtime, which we try to keep from the beginning until the end. This one here, let's visualize in the following way. Let's say I got a stack right here. Okay? Somehow V right here, since we're handling it, so it should be somehow the current top of the stack. There might be something that goes before V, right here, that just occupies certain part in the stack, but we don't care what it is. Just notice that V here is the current top. Okay? Now what's going to happen is, if we choose to go for X, that one there is going to involve some handling. Grow the stack. At some point, we can go back to V and say, we are now done with traversing this part already. So now, what should we do? You should go for the next incident edge. In that case, we're going to, let me just do a different color. In that way, you're just going to, again, extend the stack and then come back after you have done that. Right? So this part here will be that part. And finally, we get back to V again, also the current top, and then we can try to reach to the third last incident edges. And that one is going to do some part for the depth first search. that one there is going to extend the stack, do something here, and eventually we get back to the V being the top again. So now at this point, is there any more incident edge we can use from V to explore further? We cannot. So this is what we set a backtrack position for V. Okay, so here, backtrack when all incident edges explored. It's a very important concept which you will see all the time when you try to use a stack to trace. We'll do some very simple example maybe after the break, and after that we'll do another more complicated example. Okay. Question so far? All good? Okay, let's now take a short break, and then we'll do the example after the break. Okay, so let's now talk about let's do our very first depth first search example. That one's more like a special one. That's not a general case you'll run into, because you can see the graph itself has no cycle. And you basically got all the nodes that we need to be connected already. It's only one connected components. So it's a tree. All right? Let's now try to do it. Okay, that's still good enough to really do as an introductory example. Okay? There's one assumption we're making here. Assumption. We're going to visit neighbors in alphabetic order. What this means is, I'm here, starting from A. I will go for B first, because that counts alphabetically before C and D. Later on, let's say the whole branch is done. Now, I have the choice between C and D. I will choose to visit C first, because that one automatically counts before D, right, etc. Okay? But sometimes I might modify the assumption to be something else, so you got to be careful. Okay? We'll try to do maybe at least one example that will modify the assumption and to see how we should really adjust accordingly. So what we'll do is, we're going to actually gradually visit the nodes. So first of all, I visit this node here, A. As soon as I try to visit the node, I need to push that onto the stack. So let's also maintain a stack right here. Right here. So we got A. And then, so now we got a choice between visiting B, C, and D, but we're going to go for alphabetic order. So what we do is, we're going to visit to B. And whenever the edge is now leading to some unvisited node, B was never visited before. So this is something we call a discovery edge or tree edge. Okay, so this one here is called a discovery edge. Discovery edge. Okay? And just to also help you to see some pattern here, let me also label the order in which we're trying to visit the vertices. So we started with A, and then we go to B, right, so far. And of course, B should be pushed to the stack. So now A is not our concern anymore. But notice that A is still in the DFS stack, still active, just being suspended. Well, just being suspended. It's not exactly active. Okay? All right, and then for B here, we got a choice between E and F. We'll go for E, alphabetic order. So that one there, we are leading us to some unvisited node, which is E. So this will be number 3. And at this point here, we have visited E here as well, which means we're going to put E onto the stack. The next one will be between G and H. We're going to go for G, alphabetic order. So go for that. Okay. 1, 2, 3 over here. Okay. In case I make any mistake, please let me know. Okay. This will be number 4. Okay. And then we got G here. And then that should be pushed onto the stack. A, B, E, G. By the way, so far, can you somehow see any resemblance to what we did in the tree traversal? Pre-order? Yeah, exactly. It will be as if we are visiting parents first until we have to visit the children. All right? That's something we can kind of conclude right away. But you can, if you haven't really been convinced yet, you will see. Okay? So what we have seen, what we will see at the end, is really correspond to the pre-order traversal, which I think there was a slide about when we reviewed the binary tree. You will see that, or tree in general. We do parent first, children next. Okay, let's now complete it because it's so important for you to know how to manipulate the stack, right? So now at this point, you can see G here. Basically, think about G here only has this option here. However, the only edge G is incident with is already visited, is already marked as discovery edge. So that means there's nothing else that's going to lead from G to somewhere. So we say that G is finished. In that way, we're just going to pop it from the stack. And the top of the stack, it has now become E. So if you look at E here, this branch is done. So we're going to go for this branch. That's the only option. So what we do is we're going to put this edge over here, also discovery edge. That one there is going to let us visit at the other branch, H. So that would be H. And that would be number 5. All right? And then for H over here, the only edge that's incident has been identified as discovery edge already. So nothing else. So H is done. Finished. So take it out. And what will be the active edge? What will be the next active vertex? It will be E, right? So now for E here, we have already explored both branches. So E is also finished. Done. So that means now the active vertex will be B, right here. So now for B, we have done this whole subtree already. And now F. So we're going to go to F over here. So that would be here, number 6, F. All right? So now F, you can see the only one going back is marked already, right? So so we definitely should, I forgot to push it, beg your pardon. After H, of course, we'll push the F. When we first got this discovery edge, we push F. But now nothing else that can be led from F. So we're going to pop it. It's finished. All right? So far so good? Okay, we're getting there. Okay? And now the top of the stack is now B again. You can see as far as B is concerned, both branches have been visited. B is finished. All right, so now the active Y will be A. Is A finished? No, because we have only done this branch only. By the way, when I say B is finished, that's more like an informal way to say that. It's really saying we should backtrack from now. Because when we say B is finished, it's because this incident edge and this incident edge have both been handled. That's exactly the diagram I was drawing from here before the break. But I try to make some connection when you study. Okay? So now from A here, we go to C, alphabetic order, don't forget. And then we're going to go over here. And then we're going to do C here. Okay? And we're going to push C to the stack. And C is also finished because the only way to go back has been already identified as discovery edge. So that one there is also going to be pop it off, right? And of course, that one there, I should really continue with the sequence. That would be number 7, right? So now we're back to A again. So now we're back to A, and we can see one more path, right? So we're going to go for here. So that would be number 8. That would be number 8. In which case, we're going to visit D. And at the same time, push that to the stack. Right? D here. And then for D here, also finished, because no other way to go back to lead any further. Remember, as far as possible, that's really the spirits for depth first search. So D is also popped off from the stack right here, right? So now we are back to A right here. So now you can see the situation for A is almost like this, basically like that, right? All the 3 branches are done. So A here is also done. Pop it off on the stack. Stack is now empty, done. So this is saying when your graph happens to be a tree, you will see discovery edges only. That's also a nice property for depth first search. That's why I chose that as the first example. Okay? So depth first search on a tree results in discovery edges only. Okay. And somehow the discovery edges, very nice, very usefully, the tree is also a spanning tree. So you can also use a depth first search in some cases to find out the spanning tree for your graph. But that's something for later. All right, any questions? Good. We got about 20 minutes or so. Let's now at least finish one complete example together. All right. And now this time, let's do some quick clarification, very quick. Okay. So this will be another slide you will see, but I'm just going to show you very quickly about the color convention I'm going to use. This is about slide number 27, just about how we can mark the edges and also vertices. Okay. Okay. So I'll use this page as more like a recap, maybe for Wednesday. But for now, I want to point to you very quickly. So there will be only 2 kinds of edges. One is called discovery. The other one is called back edge. So only these 2. Because now the graph we're going to see has a cycle. So it is possible for us to see a back edge. But we'll see exactly how that's going to go. Okay. Okay, let's now go on to this example here. Okay, we'll just go as we learn as we go. And remember the assumption, adjacent vertices in alphabetic order. For example, let's say for A here, and also what should be the starting vertex, right? Start vertex of the DFS, let's say happen to be A. But doesn't need to be. I can easily change the question to be, let's say start vertex will be, let's say E. In that way, the way you're going to mark the edges will be completely different. It will still give you a tree, but just a different shape of the tree. Okay, so just remember that. Okay. But let's focus on this one here. Okay. For depth first search on the undirected graph, the situation is pretty simple. We actually just have to track the stack, and also we got to track about the push and pop order. I'm going to make it more systematic. And also we're going to track about the timestamp, like a sequence of marking the edges. I'll also label as 1, 2, 3, 4, etc. Okay? Let me first talk about what could be the example question I can ask you. Let's say I say in the test, I want you to start with some depth first search. And these are some example questions I can ask. Okay? So let's say questions. Could be, okay, give me all the discovery edges. Or it could be give me all the back edges. Okay, also tell me the order of pushing vertices. Also tell me the order of popping off the vertices. Okay, just some example questions. But they will all be answered once we if you do the tracing properly, which I'll show to you along the way. Okay, I'll go very slowly. It's our more like an in-depth example, right? We might just be able to do one more in the tutorial, but that will be it. Okay, but you'll do possibly one more in the assignment too. Okay. Okay, so let's set up something here. I want to have a table here where I'm going to track about pushing and popping. And then, of course, I'm going to get my stack right here. In the beginning, we say that all the vertices are unvisited. So I'll just draw them, all of them as pink in the beginning. So you can think about this one here is about unvisited vertex. As soon as the vertex is visited, I'm going to turn it to green. Okay? Let's see. All right, so we start with A. So A, as soon as it's actually being visited, it will now turn to green right away. So let me just try to get right here. Okay, there we go. Okay. So A is going to be turned into visited right here. Right? So A should be pushed to the stack right here. Okay, that's all we do. And then we have to make a decision. We got 1, 2, 3, 4, 4 incident edges. You can see we got 1, 2, 3, 4, and alphabetic. A, B first. Okay? So that one there is going to be a discovery edge because you're leading to a vertex that's not visited just yet. Okay? So what we do is we're going to have this edge over here. And this is the very first edge we mark, just number 1. Okay? And of course, that vertex will be turned into green. Okay? And we're going to push B onto the stack. All right, so far so good. And now for B here, we don't have a choice. There's only one incident edge, which will be leading to C. And C currently is unvisited, pink. So discovery edge, right? So what we do is, let's now try to get another discovery edge. So that one I'll label as number 2. As soon as C is now being visited, I'm going to turn that into a visited edge. Right here. Okay? And then I'm going to push that to the stack. Remember the spirit about depth first search. You want to go as far as possible until you actually have to somehow backtrack. Until, but not yet. Okay? So we got A, B, and C. And for C here, we got choices. We got 1, 2, 3, and 4 incident edges. We don't look at this one here because this one has been marked as discovery edge already. So we should really go for this one here. But what's happening here? It's now leading to a vertex that's not really pink, it's green. So it's something called back edge. As soon as when you're doing that first search on the undirected graph, you see a back edge, that means you have a cycle. And the cycle goes like this: A, B, B, C, C, A. That's the cycle. So imagine that if you're implementing this in Java, as soon as you see this leading to some you identifying some back edge leading to some visited vertex, you can return the that first search, maybe order so far, whatever that's on the stack. Right? You can work out the implementation detail in the assignment. All right, so this one here, we don't need to change the color for the vertices. They have been just both visited. So all we do is this one here. Okay, so this is a back edge, number 3. Okay, I would say back. And the pink one there, I'll just say the first one, discovery. Okay. All right, so we got C here. So we are now done with these two. And then we can go for another one, right? This one here, another discovery edge. Okay. We can expand a little bit further. So we're going to do for this one here. So this will be number 4. So now D will be visited. So turn that into a visited vertex right here. At the same time, we're going to push D onto the stack. Now, any idea? What should we do the next step? First of all, you want to think to yourself, which vertex should we handle now? D, right? Because that's exactly the top of the stack. So now D to A will be what? Discovery or back? Back, yeah, all right. So now from D to A is another back edge right here. Number 5. So now what happened then? So far this incident edge for D is discovery. This incident edge for D is back. There are only 2 incident edges. So D is finished. We should backtrack. Backtrack means we got to pop it off from the stack, right? So what we do is we're going to say pop it off and make a record, D. Now the vertex to handle will be vertex C. So now for vertex C over here, these 3 incident edges have been handled, have been marked already. So we still got a very good choice. We can extend further from here. All right? So that one there is going to extend to here. And that one there is going to be number 6. And as soon as we get to vertex E, it will be considered as visited. So turn that into visited right here. And then, of course, we're going to push it to the stack. So now we're trying to handle vertex E, which got 2 incident edges. This one here has been handled, but this one has not been handled. What should we do with this? Back edge, right? Okay, so hopefully you're following. Okay, right? So, this one here is going to be another back edge right here. So this will be number 7. So there are 7 edges in total, but I'm trying to put a timestamp, like a chronological sequence about which one, like the order in which we try to identify the edges. Okay. So now after this, E here, backtrack, because both edges have been handled. So what we do is take it out. And then we go to C. Again, have we done with C? Yes, all the edges have been identified. Take it out. C here. Are we done with B? Yes. 1 and 2? Yes. Take it out. And then are we done with A? Yes. 1, 2, 3, 4. All done. So you got all the questions answered here. What are the discovery edges? 1, 2, 3, and 4, which is exactly 1, 2, 3, 4, 5 minus 1. It's a spanning tree. Okay. Number of discovery edges equal to the number of edges minus 1, because it's a spanning tree in this case. All the other edges over here will be back edges. And let me give you a little bit look ahead. I think it's very nice to somehow get yourself used to just undirected graph doing DFS. And as soon as I introduce about how to do depth first search on directed graph, either maybe most likely on Wednesday or maybe after the reading week. Once the graph becomes directed, things will get exponentially more complicated. Because in the case we have to mark the edge as green, there will be three possibilities. Either the green is a back edge, still the same name, or it's a forward edge, or it's a cross edge. That's something you will have to see. But there's got to be some progression. That's why I want to talk about this one first. Okay. Okay, that's good. All right, any questions? All good? Okay. I think we have time. Why don't we do one more example? How about that? Okay. Let's now change things slightly. In principle, you will still do alphabetic order, but AC should be taken first. Meaning that, as far as this one is concerned, I should have done AB, AC, AD, and also AE, like before. But now I'm saying that, no, you got to do AC first. Apart from that, you can do alphabetic. All right? Why don't you guys take just 1 minute to see how much you can get started, right? And then I will finish this example. Okay. I'll just set up the table for us to trace. And for simplicity, let's say unvisited vertex will just be white, like no color. This will be actually very nice because the same color will be used in the depth first search for directed graph. So you can you can draw the pink if you still want to, like before, but you can just leave it white. Okay, just make it a little bit easier. Okay. I didn't tell you, but I'm pretty sure that's your assumption. We start with A. Right? Not necessarily every time. I'll make it explicit in the question. All right. So what we do is, first of all, visit A. At the same time, push it to the stack. And then we go to AC, right? That takes priority. So it will be right here. So this will be number 1, which will visit C right here. C and C. All right? And then from C over here, this one is already marked. So we go for B. Agree? Alphabetic order. Okay? So we go for B right here. So that will be number 2, which will visit B. So I'll put B here and also push it. So now for B here, as you can see, you only got 2 choices. This one has been marked. So this one is leading to some visited vertex, back edge. Right? That would be number 3. So now, as far as B is concerned, we have done with these 2. So B is done. Backtrack. So B, pop it off. So now the active one to handle will be C. So now C here, you can see we got 1, 2, 3, 4. Right? These 2 are identified as edges already. So let's now do this one here. Okay. So we'll do right here. So that will be number 4, which will visit D. And let's mark it as visited. So now the active one is D. Right? This one is already done. So go for this one, the back edge, because A is visited. Right here. Oh, actually. All right. So now D is active. As far as D is concerned, these 2 are handled. backtrack. Remove it from the stack. So we get back to C again. So now you can see for C here, 1, 2, and 3. Oh, we're leaving, so one more here, right? Oh, I forgot to actually label this one here to be number 5, right? Beg your pardon. Okay, number 5 here, okay? So now as far as C is concerned, we only got this one left, no choice. That one there's gonna be a discovery edge. So leading to E here, which has not been visited just yet. As soon as we have done that, it's now visited. So we're gonna do E here. So that will be number 6. Number 6 over here, and then we push E. So now for E here, one more left, right? Back edge. So that would be number 7. 7 edges, so that means we're done. So I would say when you are given maybe a slightly more complicated graph, first of all, calculate how many edges are in total, so you will know how many steps you will be needed in total, right? So you can somehow know how close you are to finishing. Right, so that's now maybe a series of backtrack, right? So E here, everything's done. So we're just going to pop it off. So now we go to, again, C. For C here, everything has been marked. So C here is also done. And then we go back to A. For A here, 1, 2, 3, 4 is all done. All right. Again, the number of discovery edges will be 1, 2, 3, 4. The number of vertices, 1, 2, 3, 4, 5. This, exactly this minus 1, the property we proved before. So depth first search, even though we started with in a completely different order, it's still giving us a spanning tree. Spanning tree, just not exactly the same. Okay? And I think we definitely can try something like this, maybe under tutorial this week. Oh, give me just 1 minute, please. 1 minute. Okay. We can try to do something like that. Much more complicated. Okay? All right. I'll see you guys on Wednesday.